So what's visible? Yeah, okay. Cool. So I'll start then. So today's topic for the reading group is large language diffusion models. So I've been hearing about them a little bit in the recent months. And so, yeah, I was interested into reading at least one of the papers of the many that are around and trying to understand a bit the mechanism. And yeah, that's what I will be presenting today. So the paper specifically is called Large Language Diffusion Models. It's a paper that was published at NeurIPS last year, so December, quite recently. And it's from Renmin University of China and a few research labs in China also, I assume, most of them. So diffusion, initially, it was used mostly in image, or the first success of diffusion models that we had in the recent years was with image generation. And so there's nowadays many like image generation models like Midjourney, Stable Diffusion, DALL-E, all these ones, and some also of the video ones too. They use this kind of diffusion training, which basically is this approach that has two directions. You start from your training data, you have like a data distribution, and you get one sample. And what you do is you add gradually noise, Gaussian noise in this most often, or some kind of Gaussian noise, and you slowly distort the image. And then the model needs to be able to recover step by step the image back to the full. So it's a training mechanism to try to learn the data distribution of images. And in this case, it's all in a continuous, like pixel, like continuous space. And it's been very successful. But it has not been as successful in text generation, at least until now. And there's some issues in text. The first one is that discrete versus continuous mismatch. It's not as obvious how to, for example, gradually make text worse. And you cannot add Gaussian noise to the word. Here it's as an example. You cannot add to the Gaussian to the word cat and expect to get a slightly degraded version of the word cat. So you can, that notion is not as clear how to do it. Then another issue is that there is error accumulation. So because the diffusion models generate all the text at once, it's harder to maintain the long-term coherence of the text in the sequence. It's basically a non-autoregressive model. And then there's been shown that there's a perplexity gap, that diffusion language models underperform compared to autoregressive models in perplexity benchmarks on language modeling. But there's been, papers trying to work on this. This is a bit of a timeline of previous papers, all in NeurIPS and ICML in recent years, of different approaches of diffusion language models. But the one that we focus in today is the one that maybe has tried to scale it up a bit to bigger models. Until before, they were using GPT-2 and transformer large architectures. And this JADA has gone up to 8 billion models now of diffusion training. So yeah, they're probably the largest diffusion models yet. So just to recap, state-of-the-art large language models, they operate in an autoregressive manner. So we are familiar with the mechanism. They train the model with negative likelihood over the data distribution, which can also be expressed as a KL divergence. But it relies on previous tokens, so it's a conditional probability of the token versus the previous ones that have been predicted. And at inference time, we also use the model sequentially. So first the first token is predicted, then the second, then the third, and so on. Instead, the diffusion models are non-autoregressive. So what they do is they predict all the sequence at once, and they can then iterate over that. So it can be an iterative prediction. where they try to mimic that denoising process that it's also available in images. So there's basically, the same in text, like forward process where we try to add noise to the text, usually by masking tokens in this paper, but there's other approaches too, like word replacement or other things. And then the reverse process where the model needs to try to increase when it's doing training, increase the probability of the ground truth of those mask tokens, and when it's inference, just try to predict that the correct argmax or whatever the coding approach that is used.
Could I please ask you a question?
Yeah.
Maybe. So you said before there are two steps, one forward and one reverse.
Yeah.
Why do you need to carry out the reverse process during training if the reverse process is used at inference?
So during training, to learn how to do that at inference time.
Okay.
So that's why the forward process is important to have different levels of masking, to have different levels of noise. And then during training, you're trying to recover from different levels of noisy text so that you see all the scenarios. So that then when I'll show the inference mechanism,
Okay.
you can also gradually,
Yeah.
iteratively,
Yeah.
yeah. So this is basically the pre-training for JADA. They shorten it, but large language, the diffusion with, I don't remember that, but yeah, this is the model, they call it JADA. And you can see very clearly how the pre-training works. So you have X0, which is the original data in the training data, which is just text. Then there is a sampling of a ratio from a uniform distribution between 0 and 1. So it can be a number between 0 and 1, a continuous number, which basically estimates the amount of text you are going to mask. So it's like 20% of the text or 30% of the text, 80% of the text. And then once you have that XT, which depends on the percentage that you have masked, then the mask predictor, which is just a transformer in this case, is nothing else. It can be any other architecture, but it's a standard transformer, needs to predict during training, needs to increase the probability of the ground truth on those mask slots.
Okay.
Yeah.
So it means for the mask token, so it means that we will hidden that token in the center.
Yeah.
And the output that we respect that the active to like that it will be the prediction of the token.
Yeah. Well, in this case, it's training, so that would be the ground truth, and the model is trying to increase the probability of the ground truth.
Oh.
Yeah, because during training. Yeah.
So it could be the random of the tokens, not like the next tokens.
Yeah, it can be any token. So it's not in order, like in autoregressive where you do left to right. Here, it's like any token can be, yeah.
So for clarity, that was a bit my question before. So there's no real generation as there is in reinforcement learning. It's more like a mask language model.
Yeah.
Where you don't predict or sample the tokens, you just assign higher likelihood.
During training, but during inference, there is
During
generation.
training,
Yeah.
So the reverse process is maximizing the likelihood of the mask.
Yeah. And they show that this is this loss that they have, it's an upper bound of the negative of likelihood of the data of the
or just of the mask tokens
of the whole data distribution, like the X0, so the original data.
Okay.
So they say like if you are able to push down that boundary, right, then you logically potentially also, but that depends on how much big the margin is of the bound, but
like an expectation.
General. So they just show it as a principled way of So my first question here that came already was like, well, first I'm going to have an example. So this is how the pre-training would work. We have a sentence, the cats sit on the mat. So we sample T, which in this case, let's say is 33. So that will mask those two tokens, for instance. And then the model, we try to increase the probability of the words there, and yeah. And so, yeah, that's the steps.
So it means in this example, so how the structure of the data, training data look like when we setting for this, this one?
Just a sentence in input, and then the rest is
Up to much the token.
there. Yeah. It will be the same. This is doing pre-training. You have the same sentences input and output, and you're just trying to increase the. If you are doing it in the standard autoregressive manner, you would try with the previous sent tokens, predict the next. But here there is a bidirectional attention, trying to, do that. So it's very similar to BERT. Like if you remember BERT.
It's search reverse process is almost identical to BERT.
It is, yeah.
It's just a mask language model.
Yeah. So that's my next slide. I was like, what's the difference? What's the difference with BERT? That was my question also I was making, and I tried to find out a few differences. So the first is the mask rate. So in BERT is fixed. It's always 15%. It's a hyperparameter you fix. Here, you keep sampling different mask rates so that you can try to learn to recover from different grades of noise. So yeah, train noise level is 1. Here is full continuum of noise. BERT is usually learned to learn contextual embeddings mostly, but it can be also used for text generation. But the mask language modeling was trained initially more for learn good contextual embeddings, and mask diffusion instead can generate a sentence from all mask tokens, can sample a sentence. BERT is usually inference is single forward passed, and diffusion is designed to have t iterative steps of prediction. And the likelihood estimation is the loss that they are using, they shown to be an upper bound of the whole data distribution, while in BERT is not the case. So those are the main differences. Then they show also they can do instruction tuning. So once you've done pre-training, then it's the supervised fine-tuning stage. And so in supervised fine-tuning, what you usually have now is a pair of a prompt with a response. Now it's not just unsupervised, now it's supervised. And so the objective function is almost identical. So the thing is that you never mask tokens in the prompt. You only mask tokens in the response. And so then the rest works identically the same. Like it's, so that's the only difference between pre-training and instruction tuning. And then we come to inference. So when we do inference, it's similar to the non-autoregressive approach of translation, where the decoder is starting with all mask tokens. In this case, the response is all mask tokens. And so the model first does a first prediction of certain tokens, and then there is a remasking approach. So once the model has predicted the first tokens, the S divided by T lowest confidence tokens are remasked. And then there is another iteration where some of the tokens are masked, some are kept. And then again, and so that iteration, it's a fixed hyperparameter in this paper. You do it 3 or 4 times, and then eventually you generate the full text. And that ST, so the T is decreasing from 1 to 0. And S, I think, is going in the opposite direction in maybe a different rate. And so basically that defines as a hyperparameter the number of the remask at each step, like how many tokens you remask, and it's a fixed hyperparameter too, based on the length of the text, of course. And the length is also, you do a maximum length prediction, and you can then detect the end of sentence token when it's predicted, and then you can post-process that. So it's an end of sentence token prediction. I can specify that. So this is another example of how inference goes. So if we have the same text as before, the cat sits on the mat, but now we just have the cat as the prompt, and the model needs to try to predict the next part. So iteration 1, the model does the reverse process, maybe predicts the following sentence. Then there's a remask, which masks 2 tokens, that keeps the other ones as correct.
Or confident.
Confident, yeah. Then, okay, remask, and then eventually goes to the final sentence. So this is how the diffusion process is working, where you slowly denoising the final generation of the text. So then we go to the experiments. So as I said, the model they use is a transformer. And the first experiment they do is a 1 billion model, 1 billion parameters. They have a identical transformer that can be run in an autoregressive, like pre-trained in an autoregressive manner or in a manner they are proposing, and they wanted to see if it can scale up. So after pre-training it for a bunch of iterations with equal amount of data, certain floating operation points, they have all these different tasks where they try like few shot and 0 shot experiments, and they see, yeah, quite similar. Depending on the task, maybe sometimes the autoregressive is higher, but otherwise quite similar trends. So showing that with 1 billion models, they were seeing that the model could learn similar to an autoregressive one. So then they move on to the 8 billion models. And this is, I don't know why it's a green line there, but yeah. The 8 billion parameter models. And so they had, okay, yeah, I don't know why it's there, but yeah. They have architecture similar as Llama, I think, but there can be slight variations between the 2 first columns. So Jada is the first, the approach, and Llama 3 and Llama 2, 8 billion and 7 billion, were used from like, they were pre-trained in a similar manner as they claim. Maybe some with more data, like Llama 3 was trained with pre-trained with 15 trillion tokens, while the other 2 are 2.3 and 2. But they indicate that these are more comparable approaches. They say that they evaluated under the same protocol. And then the other columns are reported from the Quen paper and the DeepSeek paper. So they are not results that they have computed themselves. And what they show in the table is that the diffusion trained with 2.3 trillion parameters is quite competitive compared to Llama 3 of 8 billion. Not better, like often actually worse, but depends on the task, it can outperform it. And it's clearly better than Llama 2 with 7 billion with a 2 trillion parameter. And then the other ones, sometimes better, sometimes not. There's a mixed bag of results. They are not claiming that their approach is better at performing all these tasks in the paper, but that they can be at the same level with maybe more efficient training.
It's very mixed.
Yeah.
Bag of results.
Yes.
In some cases, they do really well. In other cases, they do significantly worse.
Yes. Yes.
Is there any attempt at an interpretation is why in certain tasks
They do
diffusion
better.
could
Yeah.
be better?
There is one later in a different task, but not in these ones. I didn't see much of a. Yeah. But there's another task later in poetry generation that they show where diffusion can be better. So yeah, this is also after doing fine tuning in the same task. So the previous one is just with pre-training models, 0 shot, and this one, or 0 few shot, and this one is after fine tuning. So post-training, which some of them are, so Jada is done supervised fine tuning on 4.5 million parameters, and then the other models are aligned with reinforcement learning style techniques like DPO, I assume, PPO, and so on. Yeah. And here again, yeah, sometimes results that are as good as the Quen 7 billion, sometimes a bit below. So depending on the task. But at the level. This is an example of the generation, how you can see like the prediction is in different colors. So it shows the darker colors are being predicted at later iterations. So because it's generated at multiple iterations, so the lighter tokens are the ones that are predicted first, like Lily and 8 here, and the number 4, I guess those are more confident. The model is confident that those are had to be in the generation, and then the rest comes later.
And this is an example of pre-training, like re-predicting that sentence.
No, this is the answer, I think. So user is asking how many kilometers can she run in 8 hours, and the result is 72 after reasoning. So this is already a trained model that trying to attempt the inference in a particular task.
But you had said before that the prompt never gets masked.
Yeah,
So I thought that the prompt here would be the sentence called user
yes,
that would be provided as is.
yeah.
I was thinking more like a translation. You would predict the various tokens in a diffusive way.
Well, that's what's happening here. So the user is the prompt, and the answer is the one below is the response.
Sure. Now I can see better because doesn't, some parts were highlighted, and that's the response, absolutely.
Yeah, yeah.
I just thought it was the above highlighted in different.
No,
parts.
yeah. Yeah.
I just couldn't.
Yeah. So that bottom thing initially would be all mask, and then iteratively becomes into that. Yeah. Yeah.
Is that a sort of like mathematic problem?
Yeah, probably is one of the mathematical question data set where you need to
And
come.
the user prompt is like the question of mathematics.
Yep.
and the System generates the answer.
Yep.
So that's why some details like Lily can be predicted very fast in the first iteration, maybe because it's in the prompt.
Yeah. That's it. And the answer comes later, I guess. But yeah. Yeah. So yeah, then they showed this one. So this one was interesting. So the reversal reasoning. They say that certain tasks maybe require not a left to right reasoning, but maybe the opposite, like starting from the right, or maybe a different strategy where you even start from the center, I don't know, and like you observe. So they show in this, like it's a poetry generation task. I don't know about the poems. You can tell us if they are good or not.
This example means gentlemen love pretty ladies.
Okay.
So the prompt of example 1 means what is the next sentence of pretty ladies? So
Okay.
the answer is gentlemen will like.
Okay.
That is a very famous poetry type.
Yeah. So you can generate the poetry, like giving the first sentence completed, or you give the last sentence and predict what's before. So that's the forward and the reversal. And so a model like GPT-4o, which according to the websites, it's about 200 billion parameters in size, so much bigger. It does much better in the forward, even Quen 2.5. But then when you do the reversal, a model like Jada is doing better.
It's super left to right.
Mm.
Nice question.
Yeah.
I'm sorry.
No.
This is the poetry task. Is it belong to text generation? Because poetry is fixed.
Yeah.
So I think instead of generate sentences, the model actually search maybe internet, maybe some materials to get the right sentences. That also belong to text generation.
No, I think it's text generation. Maybe this is an existing poem and the model might learn to copy it and memory because of the training data contained it, but you can also generate new poems. It's not necessarily only existing ones.
But in their prompt, they're asking what is the next sentence of this sentence, then it's actually fixed in time, because it's a very famous poetry.
No, it could have been linked into the training set of these models. And therefore, in that case, the correct answer can be provided by retrieval rather than genuine
Yeah.
generation. But they normally take a lot of care to try to avoid using these in the training data or
Yeah.
RAG or so. I
Yeah.
think if they did it properly, they would have tried to not have this example.
But
Yeah.
if so, then the model's answer might be different from the original poetry.
Yeah.
But the answers are exactly the same as the famous poetries.
Yeah, but this is an example from a training data.
It feels like information retrieval thing.
It's a bit like, the arbitrarity of having a reference when you have a translation, the reference is to some extent subjective. Well, there could be alternative translations that could be as good, the same with summaries. In the end, you have to choose one to be your reference text for measurement of accuracy, and in this case, they chose the ground truth
Yeah.
of that poem to be the reference.
A little bit, still seems a little bit weird to me because every character in this poetry is not commonly used.
Yeah, but this can be from the training data. Like, I don't know if this is an example of the model prediction or example of the task. It could be just the training data, which is being used to train the model.
Example, this character is not used in current Chinese.
Yeah.
I mean, if everyone cannot see it, this
Yep.
is the example. Example one, answer, the last character is not used
Sure.
in modern Chinese.
Yep.
So this is only, and this poetry is
Well,
like
let's continue and then we can move back on. Yeah. Now,
It's like in between things.
yeah, we can come back to that discussion after. Yeah.
Okay.
So yeah, here they only showed that that the reversal process is it's performing better in the diffusion model than in the other models that are autoregressive, left to right. Then they also show that their architecture is flexible, so it doesn't have to work just a pure diffusion. Like, you can actually train the diffusion model in the style we showed, but then you can also implement the inference in the autoregressive manner, or you can have block diffusion where you reserve a certain amount of text to generate and do that in a diffusion, then the next block, then the next block. So they have like a few different strategies of inference that are not necessarily the whole sequence is done in a diffusion inference manner. But they actually show that the pure diffusion works the best. So if you trained it that way, even though the architecture is flexible, the training is being done in that way, so the model works better like that. And then this is an analysis of sampling efficiency. So this is another thing that similar to Shige's paper, you have a flexibility with Java of how many iterations you do at inference. So Java has this trade-off between generation quality and sampling speed. So if you do more iterations on trying to improve and denoise the sentence, maybe you get a better quality, but it's slower because you are repeating iterations. But you can maybe do like less iterations, the quality might be not as good as many iterations, but there's that trade-off that allows you to play with. And here this shows that, like, for example, in these two tasks, the GSM-8K and the math, the model with like much faster inference, I don't know how many iterations that equivalent to, but a throughput of 40 tokens per second have a equivalent quality of the other two models in this one and also in this dataset. Not so much in the MBPP, so also depends on the dataset. And one limitation is also memory-wise, that Java cannot use KV caching because of how it's done. So memory-wise is the same as a model with no KV caching, but these days a lot of the autoregressive models are using this, which also makes it memory-wise better for long text generation. So that could be a limitation of this too. So just to conclude, I have a few thoughts. First one is that this is very similar to non-autoregressive transformers. And I was pointing also Shige's paper as a reference there, like Lyerglad, which had a similar intuition that trying to gradually noise and a different, in this case, Shige did with the layers of the transformer, like trying to do prediction at every layer of the transformer with different masking strategies. So it's not coming out of nowhere, like this kind of non-autoregressive predictions have been around for a while. And this is, I guess, a different training strategy for that. But then also a thought I had was like token masking is not the only noise. I've seen some papers doing it different ways, but what I see the limitation if you just train with token masking is that sometimes you might predict certain tokens in fixed positions, but what if you want to reshuffle them after, right? Like reorder them, so maybe word replacement permutation could be also interesting. Other, or maybe using some proxy model to measure perplexity and do sampling with these different levels of perplexity of the text generated. Could be also interesting ways of trying to expand this training. So yeah, and it would be also good to see what other tasks could benefit from bidirectional reasoning, because here we see a mixed bag of results in the paper. So yeah, it would be better to understand when diffusion models might be better than left to right models to try generate quickly some good answer. So yeah, reverse poetry is the only one they showed, but are there more tasks in NLP that maybe this can benefit from? That would be good to see. So yeah, that's all. And here you have the references also for yep. So thank you. Maybe now we can stop the recording and we can go to questions. Yeah. Yeah.
Stop recording and discussion, stop recording, should want to stop.